31. The following equation represents a reversible decomposition, and then they give us the equation right here. And they say, under what conditions will decomposition in a closed container proceed to completion so that no CaCO3 remains? Okay, so we have the balanced equation. Let's just write it out a little bigger just so that we could work with it. So I got calcium carbonate, CaCO3, and that's a solid. And this is reversible, right? It comes to equilibrium with CaO, calcium oxide, and that's a solid, plus carbon dioxide, which is the gas. Okay, so maybe I can scooch that over a little bit. Beautiful. All right, so the key to this problem is that you want to just state what conditions will occur when you want no calcium carbonate to remain. So I don't want any more of this guy to be in the reaction, right? I don't want any more of this. So I have to figure out which reaction or which pathway am I going. Do we want a reaction where we go in the forward direction, or do we want to go the reverse direction? Keep in mind that the arrow is always going to give you more of that side, and this side is going to be less. So if we don't want any more calcium carbonate, we don't want any more of this, so I don't want to produce it, I want to go away from it. So I know that my reaction has to be going this way. Okay. So now, we almost answered the question. But now we need to force the situation in which I will produce the forward reaction. And only the forward reaction. Well, that comes from our knowledge of K's and Q's. Remember, we've done a ton of work with K's and Q's, right? The K is the standard, right? It's the equilibrium constant. And the Q is the reaction quotient, which is when you have concentrations or pressures at any time during the reaction. K is only at equilibrium. So, if I want to force the forward reaction, look at these arrows, guys. Which one are we going to do? Or what situation do we have here? If we want to go towards the product side, or we want to shift to the right, we need an example in which K, the equilibrium constant, has to be greater than the Q value. Okay, so we're almost getting there, right? So, remember, the Q is always concentration of the products divided by the reactants. And remember, solids and liquids don't count. So this was a solid, so that's not going to be in our Q formula. And this is our solid, so that's not going to be in our Q formula. The gas is the only one that's going to be in the formula. And since it's in the product, it goes in the numerator. So the Q is literally just equal to the pressure of the CO2. There's no coefficient here, so I don't have to raise this to the first, but basically the Q value is equal to the pressure of CO2. So we just need a condition in which the equilibrium constant is greater than, I could just say that the Q is the same thing as saying the pressure of CO2. So I have to basically have such a low pressure in which I cannot reach equilibrium. That's the condition. So it says, under what condition will this proceed to so that no CaCO3 remains? The condition is which you have very little, there's no exact number here, but very little partial pressure of the carbon dioxide so that basically your K can't be reached. Can't be reached. And that way, it will always be forced to make the product, and you will never have your calcium carbonate. And that's it. So hopefully this concept made sense. Let me know in the concepts. Let me know in the comments. No actual math here. This is just like a theoretical question. So hopefully the concept stuck with you guys. All right? So I will see you in future lessons. I hope you have a great day. Let's keep learning, and I'll see you later. Bye-bye.